Michael Levin is a distinguished professor in the biology department at Tufts University and the holder of the Vannevar Bush Endowed Chair. He's the director of the Allen Discovery Center at Tufts and also the Center for Regenerative and Developmental Biology. His research focuses on understanding the biophysical mechanisms of pattern regulation and harnessing endogenous bioelectric dynamics for rational control of growth and form. Now, the capacity to generate a complex, behaving organism from the single cell of a fertilized egg is one of the most amazing aspects of biology. Levin's lab integrates approaches from developmental biology, computer science, and cognitive science to investigate the emergence of form and function. Now, using biophysical and computational modeling approaches, they seek to understand the collective intelligence of cells as they navigate physiological, transcriptional, morphognetic, and behavioral spaces. They develop conceptual frameworks for basal cognition and diverse intelligence, including synthetic organisms and AI. Also joining us this evening is IRINA RISH. IRINA is a full professor at the University of Montreal's Computer Science and Operations Research Department, a core member of MILA, the Quebec AI Institute, as well as the holder of the Canada CIFAR AI Chair and the Canadian Excellence Research Chair in Autonomous AI. She has a PhD in AI from UC Irvine, and her research focuses on machine learning, neural data analysis, neuroscience-inspired AI, continual lifelong learning, optimization algorithms, sparse modeling, probabilistic inference, dialogue generation, biologically plausible reinforcement learning, and dynamical systems approaches to brain imaging analysis. Anyway, folks, I really hope you enjoy this conversation today. So without any further delay, I give you Professor Michael Levin and Professor IRINA RISH. Enjoy. Michael, it's an absolute honor to meet you. You've got a very interesting background. Now, I discovered your work when we did a show on Emergence, and I was looking into graph cellular automata, actually, and I was looking into that, the CNN version, which did this concept called morphognetic engineering, which is this idea that you can almost transgress ladders, like levels of the emergence ladder by describing something at the microscopic scale and then getting this kind of emergent global coherence. And in that particular case, it kind of emerged as the shape of a gecko. I'm not sure if you're familiar with that particular thing, but so emergence is fascinating. But coming at it from your angle in biology, how do you see the interplay between what you do and artificial intelligence?
Well, thanks very much. I'm very happy to be here and have the chance to talk to you about these things. A couple of things. I think that intelligence is baked in basically at the very bottom of the multi-scale architecture that we have in living organisms. And so what I think is very powerful is this interplay where we can, of course, use AI and machine learning to try to understand the biology better. And at the same time, we can take all of these unconventional examples of intelligence and cognition that we find all the way down to molecular networks and use them as inspirations for things that we build, right? Either hybrid systems or fully engineered systems. And I think one of the key things to say, from my perspective, is that emergence is not the whole story. So I think emergence is very powerful, and emergence certainly happens. And we have many scenarios in which highly parallel active implementation of local simple rules gives you some kind of complex emergent outcome. So we certainly see that. But I think the magic of biology isn't just that. I think the real magic of biology is that at every level, these are not sort of feed-forward emergent processes where you follow the rules, something comes out, and there you go, whatever comes out, comes out. I think that the key to understanding the power of biology is that all of these things at all scales are closed-loop, goal-directed in the cybernetic sense, not in a magical sort of supernatural sense, but in the cybernetic sense, goal-directed agents that are able to detect error from specific set points and are doing their best in terms of using energy and sometimes actually very clever kinds of policies to achieve specific goals in specific problem spaces. And I think scaling that up gets us much further than emergence alone.
Interesting. So I read a book by Douglas Hofstadter called The Strange Loop, and he has this idea of all sorts of interesting causal relations between the scales. And this is something that I find it a bit difficult to get my head around. So, the mind, for example, is an emergent phenomenon, and we have this thing called agency, and I direct my hand and I tell my hand to move. But if everything does emerge from the lower level domain, how does that work? How do you get these feedback mechanisms?
Yeah. Well, a couple of things. First of all, this notion of reducibility to the lower level. So for a really long time, for centuries, this was a philosophical debate in that people could argue they were reductionists, and they would say, well, ultimately everything's reducible, and people would say, no, there's strong emergence and things happen at the top. The amazing thing to me is that this debate has been actually moved from the area of philosophy to the area of mathematics and rigorous science by people like Giulio Tononi and Eric Hole, who have actually produced new advances in information theory where you can actually calculate which level of your system does the most work. It is no longer up for philosophical debate. You can actually do the calculation. So there are literally, there's a software toolkit that you can use, and for a given, and sometimes you will find out that yes, indeed, it is reducible to the lower level. And if for other systems, you find out that actually, no, the higher levels do more work, more causal work than the lower levels. And this has been obvious in biology, I think, for a really long time, because we as scientists and engineers, other organisms, and in fact, the evolutionary process itself uses higher level control knobs, exploits them very, very significantly. The kind of things that we, for example, study is membrane voltage. So resting potential is a kind of aggregate coarse graining of the positions of the individual ions. But you get much further in terms of regenerative medicine and other applications if you track the voltage, not the molecular details of the ions. It actually helps you do new experiments, produce therapeutics by tracking this high level thing that a reductionist might say, well, it doesn't even exist in the first place. So I think these higher levels absolutely have causal power. And the way that I would put this strange loop idea, and I think Hofstadter has many kind of ingenious concepts in his various books. The way I would put the strange loop idea is like this. Many of the things we are interested in, so memory, cognition, all these kinds of things, in my framework, and I have a particular framework for thinking about these things, in my framework are observer dependent. So when you have a particular system, the claim that it occupies some level along this continuum of agency, and I do think it's a continuum, it's not binary, the claim that it occupies some particular place along that continuum is an observer relative claim. In other words, it's not an objective fact about it. It's here's an observer. That observer can formulate some particular model of this thing as a cognitive agent at some level of sophistication. There's a different observer that has a different model, and each of them can interact with that system well or poorly to the extent that their model allows. And so where you get the strange loop is that the observer, which is necessary to define all things like problem spaces and the goals, these are all observer dependent. The observer might be the system itself. So when you get the real boot up of agency comes when the system becomes its own observer and starts to make internal models of its own parts and models that help it control itself in its own lower levels, when the high levels start to control the lower levels.
Yes, and that's somewhat reminiscent of Carl Friston. He has his free energy principle and the concept of a Markov blanket and being able to predict external states probabilistically. But yeah, there's two things you said there. So first of all, this notion of things at different levels of the emergence ladder doing different amounts of work, and that suggests to me a kind of form of strong emergence, which is an affront on physicalism. So I wondered if you could pick up on that. And the other thing you said in terms of this observer relative thing, that gets rather to this kind of ultra relativistic, or even, like in the Wittgensteinian sense or the Putnam sense, that you can take any computation, represent it in any physical system, and the meaning of that computation is in its use. So it doesn't really have any agency or valence in of itself.
Yeah. So I think that, so the first question first, I guess, it's only an affront on physicalism if you assume from the beginning that physicalism has to be ultimately reductive. So I don't believe that to be the case, and so I'm okay with a certain kind of physicalism that does real justice to the fact that. And I think, Ian McGilchrist says this. He says, a lot of physicalists really underestimate matter. Matter is amazing and it does some amazing things. And when you say, "Wow, that can't be, matter," that can't just be matter, you're not understanding what matter is actually capable of. And I think if we take seriously the fact that it can be matter, and also higher levels of organization can do work that is not apparent at lower levels, I think that's totally compatible. And I'm sorry, I forgot, what was the second part? The second question,
the observer relative. So let's say the Putnam idea of being able,
I think that's pretty necessary. I think that gets you very far, actually, because a lot of times we get stuck in these pseudo problems when you try to make objective claims about this area. You get into real problems where that resolve once you specify from whose vantage point are these things true or false, and so you get into this observer relativity. But I think it's really critical to say that the system itself is also a valid observer. So it's not just that, well, you have no meaning of your own, it's up to us to interpret you. I mean, we can interpret you, but you can also interpret yourself, and you're not dependent on external observers to define these things for you. You are also a bona fide observer. But I do think, and this is work that we've done with Chris Fields, the role of an observer in all of these things, I think in the end is really critical.
Wonderful. IRINA, thank you so much for joining us today.
Thank you. And really good to see both of you. And I'm also looking forward to seeing Michael's talk at the workshop that we're running next week at the III conference. So, I joined a bit late. So were specific questions you were kind of discussing? Well, I just caught the last one. Anything?
Well, so we just did, I'm really interested in the rungs of the emergence ladder and how different rungs do different amounts of work. They have complex causal relationships between them. Is it an affront on physicalism and reductionism? And we're also talking about this very slippery notion of agency and where do you draw the boundary, and if you can draw a boundary.
Yeah. I mean, I was saying that I don't even think that it's primarily an emergence continuum. I think that it's I call it a persuadability continuum, but it's basically it really is a continuum of agency, and I don't think there are any sharp boundaries. I think sharp categories are what we as observers bring to an underlying continuous phenomenon, and we can try to impose categorical boundaries on things that make it easier for us to do specific things. But the underlying phenomena, I think, are completely continuous.
I do agree with that. And yet there is a notion of transitions in certain metrics of behavior. I'm talking purely from kind of practical examples, say in behavior of large scale, say, AI systems, neural networks. So we know, and that's been observed recently, so that with, say, scaling the amount of data or model, you might, for a while, still not be able to do certain tasks well. And then at some particular kind of critical size, something happens, and model suddenly like groks it. So this grokking behavior have been observed over and over in the past year. And so in large-scale machine learning models, which is essentially kind of emergence of certain ability. And well, I mean, it is still continuous, but there is a change in the slope, and the change can be quite dramatic.
Yeah.
So in a sense, it also resonates with other examples where transitions were happening in AI, but not necessarily in machine learning, going all the way back to good old satisfiability problems or constraint satisfaction problems. In general, even other and hard problems like discrete problems, where you may have a network of variables or nodes that can take different values, and you're trying to basically increase the density in terms of number of constraints and see what happens. And the property of being satisfiable problem to unsatisfiable changes continually, but that probability experiences sharp drop at certain critical value of, say, number of constraints in the system divided by the number of variables. So this constrainedness plays a role of critical parameters similar to critical parameters such as temperature or pressure in physical systems, which undergo like state of matter transitions, whatever, the water to solid and vice versa. And similar like ferromagnetics, when the temperature increases and the ferromagnetic basically stops being magnetic. And the analogy was made in some cases quite clearly with those AI problems and their properties and those transitions in them. It also kind of relates closely to like random graph theory. There is a famous old theorem by Friedgut-Calais that if you consider random graph and say P is probability that there is an edge in that graph, and that probability keeps increasing. When it's 0, the graph is fully disconnected, no links at all. If it's 1, everything is connected, it's complete graph. In the middle, say if you look at connectedness of a graph as a property, what's the probability that from any point you can get to any other point and there is a path? That's what means graph is connected. That property, its probability, again, sharply goes from 0 to 1 around certain critical value of that parameter. And then any other property, what was the beauty of that result? Any property doesn't have to be connectivity. That's monotonic in age addition, will have phase transition. So though it's continuous change, the shape of it is highly nonlinear.
Yeah. So that's super interesting. And of course, there are many phenomena in physics and in math that show this kind of nonlinear change, and that's fine. I'm interested in how sharp it really is, and in particular in the cases that you talked about, because what happens in biology is that people will sort of, they look at the adult or let's say a human, and they say, okay, this human has true cognition and, real, hopes and dreams and whatnot. And then they look at the one cell egg at fertilization. They say, wow, that's just a chemical system. And so the theory is that at some point, right, so people assume that at some point there's some sort of phase transition. And a lot of people will talk about this phase transition. But if you really dig into this and ask them to specify, so what is that phase transition, right? So in biology, at least in that, and the same thing happens in evolution on the evolutionary timescale. I have never heard a plausible story of where is it. So at this moment, boom. So that thing moved from here to there. Now we have this like crazy, large transition, and it's actually quite smooth, even though people tend to assume there must be some kind of phase transition. And so I wonder, just out of curiosity, because I'm not super familiar with the examples that you're talking about, if you were to zoom in, right? So let's just magnify it. So clearly you have some sort of sigmoid. So now we're sort of zooming in. How sharp is it actually? Is there an atomic operation where I add one edge to this graph and bam, now I'm somewhere else? Like, how sharp is it really?
So just like phase transitions in statistical physics, the sharpness increases with the size of the system. Say you have any finite size graph, transition is, your sigmoid. When you grow the size of this graph, say you grow that satisfiability problem or whatever, the transition becomes sharper and sharper. So in the limit, when the system is infinite, that basically the exponent diverges. So it is getting sharper. So in empirical results, people were kind of doing in constraint satisfaction problems, satisfiability problems a while ago, and random graphs, but that was happening indeed. So as essentially in similar physical system, sharpness depends on the size of the model and or the number of units, particles, variables, nodes, while the critical parameter is another thing. And at the same value of that critical parameter, like, for example, ratio between constraints and variables, the transition happens. And then all the pictures indeed were that you see sharper and sharper and sharper or increasing number of variables in that problem. So in a sense, it behaved pretty much just like it was supposed to behave with certain physical phenomena, phases of states of matter, for for example,
Interesting.
or ferromagnetics, like Ising models.
Yeah.
It's not always like that. I'm not saying, of course, people try to exercise caution when they see rapid improvement in performance of machine learning models. For example, GPT-3. On particular tasks like arithmetic, it was observed that while on other tasks and just on measuring how the loss function during training behaves, it's used to be like quite common to observe power loss. And that was a famous Jared Kaplan's and his colleagues from OpenAI paper on basically the scaling loss behavior in language models, and then they found in other modalities. Anyway, so it's a whole field. Power loss kind of ruled for a year or so. And then people started digging into more complex behaviors because for certain tasks, like as I said, arithmetic or any discrete operation that can be described as a table, people discovered that, say, GPT-3 may not do that task well until certain size, and after certain size of the model, it rapidly improves its performance. Another example was a so-called grokking paper. Also, it was in the Guy-Clear workshop, and paper I think was from OpenAI, where they, by mistake, just left model running and training on the data multiple epochs. So they were not really scaling model or data, but just let it run. So compute was growing. And it wasn't doing well. The accuracy was kind of low. And at some point, it suddenly, later on, they saw when they looked at the process they forgot to kill, they looked at it, kind of groked the problem. And at some point, it suddenly improved first training loss and then test loss. Now, there are multiple groups very actively kind of studying this phenomenon. We got very interested back in, I guess, September 2021 and submitted a paper just now. Max Tegmark's group worked on that, and they have some papers now. Jacob Steinhardt from Berkeley, they just had accepted paper at ICLEA. So anyway, people very much got interested in grokking behavior. Not necessarily this specific example, but in general, when parameter of interest, which might be critical, increases on the x-axis. It could be a compute, data size, model size, perhaps something else. And then you have whatever performance metric on y-axis. It could be accuracy, could be loss, could be something else. And trying to understand when those sharp changes may happen and how sharp they are and so on. So we recently actually got this paper at ICLEA with my collaborators. With the first author is Ethan Caballera, and Kshitij Gupta is second author. And anyway, basically trying to fit all these strange behaviors with one functional form. It's so-called broken neural scaling laws paper, because it's much richer behavior than previously assumed just power laws. And those sharp transitions or not so sharp transitions, but transitions may happen. Anyway, so it's a bit maybe off tangent. It's about, is there a one functional form to capture them all? But what I'm trying to say, those behaviors keep happening. There is a paper, I guess, from Stanford on like emergent behaviors in language models. And they show many, many empirical examples of when this type of behavioral change happens. Needless to say, people are very interested in, well, you don't have to call that emergent behavior, but people interested in unexpected changes in performance or other metrics which may relate to like AI safety, AI alignment, like truthfulness of the system, robustness of the system, or any other property of interest. So it would be really interesting to understand better when and why behavior may change. So this broken neural scaling laws was just trying to do it as a black box, looking at the system from outside and trying to statistically predict where it happens. But many people also look inside, trying to understand what dynamics of solutions can possibly lead to and can allow you to predict what's about to happen. So actually, our studies, it seems to be related to certain oscillation frequencies in the training laws, but you might be able to tell from the beginning of the run for given initialization of system if it's going to grow or not, which is good to know.
Yeah, no, I think it's super interesting, and of course, I'm not doubting that these things exist. What I don't know is to what extent these are good models for what goes on in the biology, because the biology seems to be quite continuous, right? So these may be two different ways to look at this, and also my sort of the reason I emphasize the continuity is not that I want to minimize the importance of great transitions, because I do think, of course, there are great transitions in behavior. What I want to do is emphasize the continuity of substrate, because a lot of the discourse, the human does this and the human does that, and they say, okay, so which kind of human, like how far back? And you can do this in evolutionary scale, you can do it in developmental scale, right? But eventually you follow the human back and you end up with a single cell, and we just have to deal with the fact that there is no magic bright line that somebody can draw. Okay, boom, at this point in embryonic development, like that's it now. And so what we have to understand, of course, there can be non-monotonic, non-linear changes and all that, but it's a transformation of the exact same substrate. It isn't something magical that gets added at some particular point and then everything else. So I'm sort of all about that aspect of continuity. It doesn't have to be linear per se, but we have to come to grips with people who think that it's crazy to attribute, they say it's anthropomorphic to attribute certain kinds of cognitive claims to a single cell. They owe a very specific story of how you get from a single cell to a human. You can't simply say that, there's some magic that happens in the middle. You actually have to lay out what is it? What's the phase transition actually? And people sort of assume there is one, but I've never heard of one. I've never heard of a good one. And so it's quite interesting to me that these do come up in the machine learning world. It's interesting that these come up.
But there is still continuity, because you essentially, to some extent, the x-axis is not exactly maybe absolutely continually growing the size, but for all practical purposes. So the curves are usually always continuous. There is no discontinuous jumps, but continuity with kind of different, speed of development, those things change. And but I basically agree with your point completely that there is no magic sauce or ingredient, unless you believe in divine intervention or something like that. But if you kind of keep this hypothesis as more complicated and prefer simpler based on just things you observe, then indeed there is continuum of intelligence from human and back to the cell. But then, of course, a good question is, like, if you start decomposing cell and go deep dive inside, then what?
So we and other people have looked at this, and in fact, if you look at something as ostensibly mechanical as a gene regulatory network, right? So you just look at a model of genes turning each other on and off. We and others have shown that kind of thing is capable of 6 different kinds of learning, including associative conditioning, just from the dynamical systems properties of the gene regulation, nothing else. So there are, and now I was just looking today, there is apparently a literature on chemotaxis in individual molecules, and which some of these things,
but
individual molecules, right? And so and then you can go below that, and the kind of stuff that we've done with Carl Friston and Chris Fields, and really start looking at very fundamental particle interactions as having sort of extremely kind of primitive levels of non-zero competencies. So it's a really good question, right? If you have a continuum, so the question is there a zero, right? Is there anything?
Right.
And Chris and I have talked about.
Is not intelligent.
Yeah. No, that's a great question. So Chris and I have talked about this, and because my claim is this: if you think about what would the absolute minimum of intelligence look like, right? Like what's the absolute minimum? And so to me, I would, if I had to come up with the absolute minimum, I would lean on two things. I would say the first thing is some level of goal directedness, some ability to pursue a particular outcome out of a set of other outcomes. And we have this in least action principles and even in particles. And then some level of indeterminacy such that local conditions don't fully determine what this thing is going to do. And we have that in particles. And so I would claim that it doesn't actually bottom out at zero, even at the atomic scale. And so I said to Chris one day, could we have a world with no least action laws, that where it literally would be zero? And what he said was, yes, but it would have to be a universe in which nothing ever happened. So it would have to be a completely static universe, that one in which things happen. You're going to be able to derive some sort of least action kind of thing, which looks like the basement of cognition to me.
Yeah, very interesting. So it was always kind of an open question how to link this to what people are, say, doing right now, developing like artificial neural networks and those systems, basically how that would translate in AI domain. What would it mean for this modeling? Like, can we indeed, well, I mean, I think people did try to define intelligence and its units, although it's not something that people commonly use. I wouldn't claim that there were no such attempts, but nevertheless, I mean, we're still not really doing that. And here and there, people say, well, probably should be measuring more formally what we want from our model in terms of intelligence and like how those things compare. And can you say that it's as intelligent as like that type of the organism or this or, yeah, so some basically making this whole engineering field a bit more of a science, like, well, physics or even biology, in terms of, in order to make claim that something is intelligent, would be at least good to define it more formally. Again, going back to physics and have some notion of units or something. So you can say that in that units, you can say this is larger than that.
Yeah. So
something like predictive accuracy of models can be a proxy for that.
Yeah. So Chris and I tackled this in a recent paper, starting off with the idea that making claims about something, the intelligence of something, is really taking an IQ test ourselves, because you have to be smart enough to pick a problem space and identify the degree of cleverness of the policy that the system is following in that space, and you may not see it, right? It's not obvious that we can always detect it, and so in biology, we are very used to seeing mid-sized objects moving at medium speeds in three-dimensional space and saying, "Oh, look at what that crow is doing. That's intelligent." But there are other spaces, right? So physiological space, metabolic space, transcriptional space, anatomical morphospace, which my lab studies. Cells and tissues do amazing things in those spaces that are absolutely, if they navigate those spaces in a way that if we had a robot or an autonomous vehicle doing that, this would be off the charts performance. And it's not in the domain of classical three-dimensional behavior. It's behavior in these other spaces, and learning to recognize that is very hard for us, because as humans, all of our sense organs sort of tend to point outwards. If you had an innate feeling of your blood chemistry, you would know without a doubt that your liver and your kidneys were intelligent, because you would see how they navigate that space. You would directly feel it the way that we currently see each other navigate and say, that's pretty clever, So what we try to do is to lay out. And it goes back to like the 40s. Wiener and Rosenbluth had this scale, right, of from all the way from passive materials all the way up to second order, like metacognition and whatnot, and everything in between. The kinds of competencies that different systems have in navigating these spaces, and one way to do it is, and I repeat this quote a lot, and I wish I could remember who said it, but somebody said this. It's the continuum between the way that two magnets try to get together and how Romeo and Juliet try to get together, right? What's the difference? The difference is in the degree of ability to overcome obstacles along the way. So you can be extremely simple, and all you know how to do is go down an energy gradient, and magnets can do that. Or you can be extremely complex and be able to. But in the middle, there's all this stuff, right? And so you can kind of start, and this is what we do experimentally. We put these systems in ways where we start to challenge their normal behavior, and we find very surprising things that people always thought were like hardwired and just sort of this. Well, of course, this is it's all it knows how to do. This thing's rolling downhill, and that's it. Once you start to challenge it with various perturbations, then you get to find out what it actually knows how to do. And then you can form specific hypotheses. Does it, how far ahead can it plan? Does it see? Does it have a memory? Does it, you can, but the way you find out is by challenging all these things. And, like the frog face example and many other things, you find out that these things are actually way more clever than they seem at first, Yeah,
I definitely remember how you gave that talk in December 2018 at New Rips, what bodies think about, and the message to people studying neural networks that, intelligence was there way before the first neuron appeared. So maybe we should look, but still the common part was networks. They doesn't have to be neural. They don't have to be neural. But essentially, I do remember all these experiments were essentially about changing the network communication so that the organism as a whole or the part of it changes its form to whatever you kind of wanted it to be. But I think even if we scratch neural from that, the key essence of kind of phenomenon will be always network.
I mean, I would, yes, but I would extend that to say that it can't be a single level of organization, right? So in biology, the trick is that every network is a network of networks, and each one is as goal-directedness. So every level is trying to accomplish specific things in specific spaces, and they all cooperate or compete with each other. So this is another talk that I give sometimes. Why it's called "Why Robots Don't Get Cancer," right? Why don't our robotics get cancer? And it's because they're not made of parts that have the capacity to go off on their own and do their own thing. In biology, every single part is basically being held against its will by the level above. So everything, if you were to just release the top level's goal directedness, the parts would go off and do other things. And sometimes they do, and we get phenotypes like cancer.
I remember really well. We've had this 5-hour discussion in the IBM research cafeteria in Yorktown a few years ago. And that was really very insightful, making analogy between kind of the cell going cancerous or coming back to its senses. And essentially the notion of at what scale the objective of the cell to survive and thrive is applied. Because, if you single cell in the environment, you treat it as a source of food. It's environment, right?
Yeah.
But if you become part of the organism, you're under pressure to behave in the best interest of organism. If you forget about that due to changes in your communication with other members of organism society, then you start acting selfishly, and too bad, that's cancer.
Could I put a quick question to you, Michael? Because I'm very interested in the definition of intelligence, and you're saying words like goal-directedness, agents, planning, and these terms are a little bit anthropomorphic. You could argue that they are universal primitives, and you're also talking along the lines of intelligence being almost like, some people describe it as capability or with an underlying principle. But it's almost like it's a continuum. And there are people who believe that humans are special. We think, the behaviorists thought that it was just a very simple stimulus response. The monkeys don't have a flash of inspiration. They don't plan how to get the banana. We have something different. What do you think?
Well, I'm certainly not saying that we don't think, or that there is no material difference between us and let's say a paramecium. So the differences are of course real. I insist on one thing, and then I have hypotheses about other stuff. The thing that I insist on is that when we make a claim about the level of cognition of some system, real, artificial, evolved, artificial, whatever. You cannot make those claims from an armchair. You have to do experiments. And so you cannot have feelings about these things. People say to me all the time, oh, well with xenobots, well, it's frog skin. That can't XYZ, you name it, whatever. It can't. I say, well, how did you arrive at this conclusion? You cannot just have feelings about this stuff. You have to do experiments. And when you do experiments, as we found and other people have found, you get surprised because it is not obvious what the capabilities of something is until you start to perturb it and see what happens. And the thing, and to find out. So in order to make an intelligence claim, you need a couple things. You need to pick a space within which you think it's solving problems, right? So you as the observer have to say, I think this is the space in which it works. Then you have to say, here is the goal I think this thing is pursuing in a cybernetic sense. And then you have to say, and now I have a hypothesis about how clever this is. What can it do? Can it go around obstacles? Is it trapped by local minima? Does it have path history? Does it have this, that? You make some sort of claim. Having made those three claims, we can then empirically see how well does that work out for you? What does that enable you to do? And so then multiple observers, so someone can come along and say, you're crazy, this thing doesn't have any of that. Somebody else can say, oh no, it's actually much more clever than that. And then we all interact with the system and we see who wins. It's an empirical question that has to be put. So the only thing that I insist on is that this charge of anthropomorphism, it has to be quite specific. We have to make a specific claim. What do we think this thing is able to do? And then we get to find out, is that a useful lens onto the system or not?
Okay, but just a quick follow-up. I mean, what is a goal? Because a goal feels like it's a wicked form of reductionism along the lines of what we were talking about before. And even because, Shane Legg has this idea that the definition of intelligence is an agent being able to solve a variety of tasks in different environments and so on. And even if there were such a goal, why would it be intelligible to us?
I don't believe that there is an objective goal that is intelligible in the sense that we get to discover it once and for all and then we're done. I think that when somebody says that this system has a particular goal, what they're saying is they have discovered a lens, a perspective on the behavior such that positing that it has a goal and some set of competencies to reach that goal gives you increased ability to predict and control that system. So we come across a thermostat, and you look at this thing, and you're a reductionist, and you say, well, okay, I can sort of calculate what all the particles are doing, and that's great. And I look at it and say, I see this, and I think this is the set point. And you say, there's no such thing as a set point. There's just atoms in the thing. And I say, well, here's the thing, though. I will exert much less energy and effort in changing the temperature of the room while you're running around pushing on all the individual, atoms of this thing. I'm just going to change the set point and let the thing take care of itself. So the level of what it affords you is a more powerful level of relationship to the system. For simple systems, that's prediction and control. For complex systems, that may be everything from training to friendship to who knows, for complex systems. What we're looking at is what level of agency gives me the best interaction with the system. And I can guess too high, right? If I'm standing there arguing, pleading with my thermostat, here are all the reasons you should change. Like, that's not going to work. And at the same time, if I have a system that's a learning agent, like a horse or a dog, humans thousands of years ago figured out that you don't need to know the neuroscience of what's between their ears. You can train the thing, and right. So you found an interface that allows you to do amazing things, because you understood that this is not the same as a complex set of bowling balls that you would have to engineer bottom up. So that's all. These things are just meant to be. I don't believe there's anything. I don't believe there's any such thing as anthropomorphism. Anthropomorphism sounds to me like we're still working with a Garden of Eden story. That you've got the human. The human has this magic glow about them, and trying to sort of shade that into other things is a major transgression. I don't buy it. I think that what you have to do is you have to make very specific claims. This human or this robot or this cell can do X, Y, Z. And then we find out it can or it can't, and then we sort of empirically we know, did we guess correctly? Did we overdo it? Did we underappreciate it? In my experience, we tend to underappreciate intelligence way more than we overappreciate it. That's just what I see in the biosciences.
Yeah, I do agree with the point that it's perhaps humans' ego would like to think that there is something absolutely special in humans, and that's on. But indeed, I mean, the continuum is there. So, and humans developed from something much simpler, and they inherited properties of that. And yeah, so basically, I think it's much better, probably even for the field of artificial intelligence. It would be much better to look at the intelligence from this perspective, rather than from the, well, as you said, Garden of Eden type of uniqueness of human abilities.
I
or
mean,
intelligence being just really bound to being human.
Yeah. Yeah, I mean, I'm certainly not arguing that humans have some interesting capacities that are hard or impossible to find elsewhere right now. But this way of thinking about them as natural kinds, as sharp natural kinds, I think is philosophically really problematic, because biology is so. I have this diagram that I sort of beat people over the head with, and it's got like a standard human in the center, right? And then up above is a very high resolution evolutionary series going all the way back to, you name it, some sort of microbe, right? And so whatever you think this human has, you have to tell me where it peters out. Like where did you have these two parents that were not whatever, right? The agential, and then bam, they had a child, and now the child has, true whatever, right? Like where is that line? That's impossible. Then down below, it's got the same sort of thing developmentally. So again, I could take you all the way back to the single cell oocyte, a little pile of chemicals, and you have to tell me where things peter out if they do. And then laterally, it gets even worse, because in one direction, what you can do is biology is so interoperable, you can start to make chimeras and hybrids between biological tissues and machines. So we can make I can have over here somebody that's 99% human and a little bit of chips in the brain, right? With some AI. Over here, it's the opposite. It's 99% Roomba with some human brain cells living in it that sort of are instrumented to it. And we can fill in every single point in the middle. Every point in the middle is occupied by a possible being, 50-50, 60-40, you name it, right? And if you're saying this is a machine and this is a human and these are binary categories, then you got a real problem telling me where we're going to shift over, right? Where are we going to click over? And the same thing on the biological, the bioengineering. And so here's a human. At some point, we're going to want some gills, and somebody's going to want a tail, and somebody's going to want a third brain hemisphere. All of this is completely doable. And we could do much of this tomorrow. And so. Then again, you have to tell me where are they? When are they not human anymore? I feel like these categories are treating them as natural kinds is limiting more than it is facilitating for ideas in this field.
Well, we very kind of clearly going into transhumanism,
yeah,
which is indeed quite a natural progression. Because you keep extending your capabilities with any kind of automation or tools, starting from glasses or whatever. And you keep extending yourself, you keep morphing with it. And indeed, it's a good question. Like, okay, so where is the line? There are, of course, many interesting, controversial questions about that. We probably should not go into that because it's kind of worms about the ethical side of all the things that we discussed. I can only imagine questions coming from that side.
One of my favorite stories I came across is the first guy to use an umbrella in London, right? I mean, this was considered scandalous. He was pelted with garbage because he was upsetting the natural order of things. So who is he not to get wet? This is unnatural. We're all walking around under the rain getting wet. And look at this guy. There was an umbrella. And right. And so, I
didn't know this story. It's real.
Yeah.
God.
Well, look, I got it off the internet, so maybe I assume
okay.
It's who knows?
I'll definitely use this story in some of my arguments. Thank you.
People, I get this from people all the time. Oh my God, it's unnatural. Look, natural is getting scratched in the forest, getting an infection and dying because you don't, because you got scratched or because we don't know how to brush our teeth. Like natural is terrible. Natural is absolutely terrible. And we can do better than this. And I think that, all of these things are going to be, people are going to laugh at us in the future, I think, thinking about the things that we were concerned with here, the same way that we think of, back in the day, the first person to come up with some crutches or some, for glasses. I mean, forget it. This kind of stuff. It's just, yeah, I don't know.
Yeah, that's a hilarious
flash of inspiration.
Yeah.
Another argument could be, well, what is really natural? Like, if we are natural and naturally our brains are coming up with those extensions, they are natural, therefore, as well.
Sure. I think all of this stuff, I think even in very modern, sort of scientific thinkers, a lot of this stuff goes back to a Garden of Eden view. If it was the case that somebody has prepped all of this for us in the best possible way, then of course the answer is, hey, you scientists, don't screw it up. It's already as good as it's going to be. All you're going to do is make it worse. That made sense when people thought that this was all created for us in the best possible way. That picture, that story has crumbled long ago. There's no way, I think, rationally to look around at the health disparities worldwide, the incredible suffering due to disease and aging and everything else, and to say that, well, natural is fantastic. Let's just make sure that, okay, natural is horrible, and up until now, there's been no way to get around it. Now, finally, we have, we're the adults in the room now. We have some ability. Of course, we're going to mess things up too, of course. But we have now some ability to do better than natural. And let's just remember that natural is not someone has prepped this for us, in accordance to our values of happiness, of fulfillment, all that. Nobody's done that. Evolution optimizes for biomass, basically. Like, that's it. It doesn't optimize for intelligence, really. It doesn't optimize for happiness, for any of those things. Evolution just makes sure that the next observer is going to observe a bunch of stuff, running around and interesting things. That's it.
I really vividly remember when you first shown the videos with those flatworms, the proverbial flatworms by now. And essentially, once you get the two-headed or three-headed, and those kind of tractors in the space of the dynamical system, they're stable, right? They replicate and they are still two-headed. And essentially say, well, one-headed worm was a solution, some local minimum, found by evolutionary stochastic gradient descent, or you name it. And it could have been another solution and another solution. And some of them maybe have lower loss or higher reward or whatever, right? Mm-hmm. So why won't we just look for them? Yeah, so that was quite an eye-opener, yet it's very strong bias against transhumanism quite often. And, it's understandable because the chances of kind of screwing things up are definitely non-zero.
Sure.
But they are also not 100%.
Yeah.
I think the difference between people is in their kind of estimation whether the glass is half full or half empty.
It's that, and it's also, so I get a lot of phone calls every week, and I get two kinds of phone calls. The young, healthy people are calling me saying, knock this off. It's like, it's scary, it's dangerous, whatever. The people with various medical problems or with children with medical problems call me yelling, what's taking you so long? Like, hurry up. We have problems. Like, we need. And so, and I just always want to try to connect these people to each other because everything's all well and good until you need to go to the doctor. And then you hope they figured some of this out. It's all scary until you need something. And
just something real and much scarier happens to you.
Yeah. And
then
it's just
stop being scared of imaginary things.
Yeah, that's exactly right. Yeah. And change, change is scary too. And the interesting thing about change, the fundamental change, is that your values can change. I distinctly remember being a young kid, looking at some of the older kids and thinking, wow, and they were they're dating and all this stuff. I'm like, oh my God, I'm gonna have to. Based on what I see here, I'm gonna end up like one of them. and then I'm just going to be interested in all this kind of crazy stuff that I have zero interest. This is unbelievable. What, is there a way to like not do that? And of course, but then of course, once you make that transition, you think, well, that was dumb because now I like all this stuff. And so you can, it's scary because when you change, the things that are important to you will change.
Yeah. Well, the good thing is once you change, you will not care anymore about the values you had before you changed.
Exactly.
So at least you will go along with that. Because I remember like before I had first child, like everybody would say, oh, now you're going to be crazy busy. You will not have time for work. Forget about friends. You'll just have no time for anything. And it looked like, oh my gosh, it's awful. Then you transition and say, well, but I don't care about that stuff anymore.
Right.
I care about this and I'm happy and have it. And that's it. So, yeah.
Amazing.
Yeah.
Amazing. Well, Professor Michael Levin and Professor IRINA RISH, it's been an absolute honor to have you on today. Thank you so much.
Yeah, really fun.
Thank
Thank you so much. Good to meet you. See you, Irina. Good to see you.